Right. So thank you for agreeing to present. Let you start.
Yeah, you can see this slides there, right?
Yeah, everything's perfect.
Right. So I'm Seokhyun Choung from Seoul National University. I'm in Department of Material Science and Engineering. And here's Hyuk-Jun Lim, who is one of the leading architecture development participant in this work. And this is my second slide, which is the title slide. I made it simple as the title I gave you was quite long. And my talk today is going to be how we can distillating a model, machine learning interatomic potential MLIP for scalable catalyst discovery. So let me begin with very basic question. Distillation. I'm of course not talking about how we distillating a whiskey. I'm talking about how we can compact a sized model into a smaller models. We call them student model. And let me share how I started this work and how we designed the architecture to shrink the model into a smaller size, and we can expand into variable variety of applications we can think of. So as a chemical engineering background person, I'm really interested in designing a new catalyst. And catalyst here can be applied for play a really important role in clean energy source and from carbon intensive energy source to clean energy source. And here with the solar, wind, hydropower, with the chemicals that is not valuable, we can transform a variable products like ammonia or CH something or hydrogen so that we can run a hydrogen-based cycle in the social. And as a computational person, if you're trying to design a new catalyst, and if I want to expect or predict a catalytic activity of one system, I'm taking the density functional theory, which we design this kind of three model system with the absorbate absorb system, a surface, and gas. And each of the system is calculated using the Kohn-Sham equation to solve the energy of each system so that we can get the absorption energy of one system. And as you might already know, this catalyst combinational space is enormous, like universe. And as some of the example I will showcase is that for the one combination, nickel and gallium, there's a 70,000 possible absorption structures that we have to calculate. So 70,000 DFT calculation is not really sustainable. And there's another example, Open Catalyst project. They showcase that 1 million.
I think we're like your full screen got lost. Oh yeah. Okay. Yeah. Are you in full screen in your screen?
Oh yes, I do.
Can you represent?
Oh yeah, sure.
Right now we see the PowerPoint, but see the PowerPoint screen. Maybe you just need to share the. Oh yeah, perfect.
Yeah, perfect. All right.
Thank you.
So let me start from here. So there's a 70,000 combination we can think of for bimetallic combination of nickel and gallium. And of course, calculating all of them, the DFT calculation is not sustainable. And there's another example by Open Catalyst project where they perform 1.2 million DFT calculations, relaxations, and producing 2 billions of structure. And they said in the paper that this is extremely sparse sampling of possible combinations. So let's say we're screening 200K Berg, starting from the Berg structure of materials project and making into a surface, and just attaching 5 absorbates on 100 sites, then it'll cost 138 gigawatt hour, which going to be 1 day of Seoul electricity usage, and it could be 4 days of Gagi electricity usage as well. So this is definitely not sustainable for discovering a new catalyst. So people is, of course, thinking of this new method, machine learning interatomic potential, where we're stacking the DFT calculations and transforming into a node and edge formation into a graph and training a transformer and some neural network in depth. Then we will find a way to get the energy and forces that we are always wanting from DFT calculation. And once we have well-trained MLIP checkpoint, then we can, of course, predict a system in few seconds. And that's magical so far. And we've been seeing that many of DFT calculation databases now applicable and now open sourced by many of the projects like Open Catalyst project, Materials project, as well as some of the contributions from Enthalpic as well, LeMaterial. And based on that, now we are seeing the Cambrian explosion of MLIPs, that we now have a practical question, which model going to be good for each of the system that I'm interested in. So at first, we made this CatBench benchmark framework where we can testify each of the different systems of where which of the model is trained on which of data and which of the MLIPs are with the different architecture. So we made this failure detection method to see whether the MLIPs are succeeding on one system or not, and based on the reproduction of MLIPs and on physical relaxation behaviors, as well as observed migration and energy anomalies. And based on that, we can see this direct correlation where the accuracy is getting better and better, of course, but the time it takes is very large for MLIPs. So before I move on, I also made this CatBench ORG with Jinung Moon and Uchan Jun. And this benchmark, we are testing different system with different observed and different surfaces. And based on that, we were quite confident that we can measure the methodology of MLIPs. However, now what we are witnessing is that from the small models like CGCNN 128K to now UMA is 1.4 billion parameters. So I took this plot from Materials bench today early in the morning, and you can see the clear direction where as the parameter is increasing, like this blue line, the accuracy is getting better and better. So this clear exchange can be also seen in this plot, where the time it takes is becoming larger and larger as MLIPs are developing better and better. So now we have better MLIP, but it takes too long time, and still the accuracy is pretty good for when you are considering the MACE models or UMA and 7net. All of those models are pretty good, but the speed is quite very slow. So we need to find a sweet spot where the accuracy is good enough while the time it takes is low enough. So I took the idea from large language model, of course, where distillation is one of the key things they usually do in large language model field, where there's a popular paper by Professor Hinton, where one of the ancestor paper of neural network distillation paper. And based on this paper, we are seeing many of the distillation in large language model, like DeepSeek is also distillating for Llama and Kuan, and they showcase this very well in their paper. And when we think of distillation, we can think of two types of distillation. One is the distillating the output of teacher and training this output into a student model, or ideally, if we can see the latent space of the model, then we can train a model with the latent space of teacher model. So taking this into a machine learning interatomic potential, now we have to think how the model itself and latent space is looking like. So let's say there's a equiformer where it is well trained, let's say. I took this equiformer V2 trained on OC20, and it has 153 million parameters. And as the molecule is passing through the latent space of deep layers, which is 22 layers in this case, their information is getting rich and rich, and finally getting the energy and first. So what we thought is that if we take the last layer, the information of a machine learning model is well reached in the last layer. So if you can take the information from the last layer and get the information from the vector of last layer, we can train a model with the information of teacher model. So taking this teacher model as a background, when we're training a small student model like this low layer of neural network, we can inject the teacher model's relational vector in some possible way. I will explain this in detail later. And let's say, excuse me?
Yeah, I have a question, very quick.
Oh, yeah.
So when you talk about the Hinton paper, so in that case, I assume they're distilling on logits, right? And this is fully the output of the neural network, and they don't have to know what the architecture of the neural network is. Like you can take anything and distill it because you only care about the logits. Obviously, I assume it works better if you have like a shared architecture. And in our case, it's like we're predicting energy and forces, right? And you're doing the analogy of we want to distill the latent space. But why can't we like do something similar than in the paper and just take energy and forces and naively distill them?
Oh.
Is that something that doesn't work?
Oh, it does work, but the point is that for that to be work, the scale gonna be large. If the scale is possible, then it could work in some ways, but we have limited scale by the teacher itself. So what I think is that UMA still, it is 1.2 billion. The scale itself is not big enough as large language model we are seeing in the Claude and GPT. They're like trillions and larger than our models. So if the scale is based, then we can try that as well to directly output distillation like I showcased in here. But the better case in ideally, if we can see what the model is thinking, we can latent distillating. So this is the option we are taking at this moment. But 10 years later, maybe we can try the energy and first direct distillation as well.
But I assume that like in images too, you can have a vision model that's not necessarily that large, but it still gets distilled with the logit. And that works pretty well. It's like still output distillation, but not massive scale as language models. Still like I assume a few 100 million parameters. But yeah, I mean, the thought is more that like, is there a lack of information in the output in our problem that isn't in a classification problem, for instance?
So there's a important point is that in the graph-formed molecule and this inorganic structure, what we really care about is the equivalency of the system, and it's not the scalar value energy only that is we are caring about. What we are caring about is the relaxation process itself and how physically meaningful the model is predicting. So to take all of this, that energy balance and the force relation between energy and force, then we have to think of the graph itself. And that's why we focus on how we are giving the information from the graph into a graph. And that's why we come up with the latent distillation at the end. So it might work if we can try as what Asian people and Logit people is doing the same way. But that's the basic idea.
That's a good point. I think there was also, I mean, one way you can distill is because it's like forces are still graph level property, right?
Mm-hmm.
But we can also see energy as like there is this pooling that's done at the end.
Mm-hmm.
And I think it's been tried, right, to distill the outputs of the model, but on each node for the energy before the pooling.
Mm-hmm.
And that's more model related, right? It's like maybe a good proxy for the logits, because it's something that the model has learned that's not physical in the data, but that can give more information. I'm not sure if you've tried that, but
yeah,
just
definitely. I will try it. That we can try it as well.
There's a comment that if we do that, we lose relational information. Yeah, and I think that's correct. But I assume that like the point of like the way it works with yeah, in that case, there is structural knowledge that we want to take from the teacher. That's a good point. But even in attention, like when we're distilling an attention module, there are relations that the teacher model has learned, but the naive distillation using logic does not care about the relations that the model has learned.
Mm-hmm.
And it's like we let the teacher learn that itself, but we're giving it something easier than the data.
Mm-hmm.
Anyways, I'll let you continue.
Yeah, I agree with that. And yeah, we are afraid to lose the information from the teacher. And what we really care about is transforming the teacher's knowledge into the student itself. So that's what we cared mostly. And so after having teacher, and what we are trying to match is the prediction of teacher. So when we're training a student model, we do a one forward pass for each of the molecule or some of the data that we want to train on. And by forward pass, then teacher model will generate a vectors of node and edges. And this information from the node to node is in the form of vector. And these vectors are now the subject of training in this case. So let's say student is predicting this vector for this methanol, and teacher is predicting this vectors for methanol. Then we are trying to constructive learning on the vector difference between the node vectors of student and node vectors of teacher. And the reason, and this forms a Rust function where it is a kind of inverse way of making the Rust function. And we're putting in the exponential form like this, so that the minimizing the vector difference between the teacher and student is valuable for training a model. And let me explain this later in the next page. And the tau value here is determining the smoothness of this loss function, and this can be implicated to the stricting of teaching. So if you're putting high temperature, then the cosine similarity is becoming larger and larger, so that the teacher is more teacher's information is more directed to the student, but the embedding error is not really. So there's a sweet spot on tau value, temperature, and the embedding. So it's plateau at some point of the temperature tau and the accuracy and cosine similarity. So it's not always putting more stricting teaching from the teacher to a student is better. So
I have a
did you
very
raise your
naive
hand?
question. Yeah.
Yep.
Very naive question. So here you're framing the problem as a contrastive learning problem, but why not view it as just a simpler problem of we're distilling the teacher feature? So why not do, I don't know, a distribution matching on the latent space or an MSC loss?
Oh yeah, perfect question. So of course we are not the first person who tried to distillate a MLIPs. So there's a two important contribution beforehand, which they tried the node embedding match of prediction, and another group tried to Hessian distillation Hessian loss function. So they formed a node information as the only loss function. In this case, they put Hessian vector as a loss function. And they're both sides of they're both sided, where this node is very easy to get and the training itself is very light. However, the information of edges are almost missing in this case. However, when you take the Hessian, the information of edges and node is very information rich. However, when we train them, it is very computationally resourced. So that's why we come up with this Angular information, so that is balanced between the Hessian and the node information, and that is the basis of what we're trying to do. And the reason we focus on each of the systems, as DFT calculation data have millions of components, and we took each of the vectors and tried to match each of the cases, and that's basically what we are trying to train during the batches of training. So that's why we focus on each of the components when you're trying to train a model.
So if I understand, if I understand well, in the case of the arc loss, this is we're saying that node I in student and node I in teacher should have the same embedding, but they should be different than node J. Is that why it's a contrastive loss? And is that what, like, where the negative push comes from?
Oh yeah, almost. So this point-wise end-to-end is the matching between the node and node. So teacher node versus node. And in this case, what I matched is the nodes to node vector. So that's why we call them Angular. It's not really Angular, but that's why that's how we can make it into a kind of. You remember the last week's this paper study? There's they try to make a general embedding method for every models, and that's why we take the relational vectors. And
so you're doing distillation on the, not on the latent itself, but on the vector that links to nodes.
Yeah, the platonic representation. I just got the word from
the platonic representation, and you're trying to align the
relational
like vectors. It's like right. Thanks.
So implementing them is really easy. This paper was done before Claude Code got famous. So we did it with our hand and very poor GPT-4, but the training itself is really simple. So usually when we are training MLIP, we are training with the energy and force loss functions. Now we are putting the end-to-end loss function and the arc loss function. And the arc loss function, the formulation is only 10 lines of code. And when we are supervising this model, when we're training, we're just adding them in for loop and adding this loss function of the Angular information and the end-to-end information, as well as force and energy. And this is the whole scheme of training, and you can check this out in this GitHub page. And
question.
Yep.
So here, like, you have 3 or 4 loss components.
Mm-hmm.
Do you keep them on all the time, or do you have like arc loss at the beginning and then energy and forces afterwards, or like, do you just
Yeah, we just wanted to prove a concept of this concept, so we didn't really overlapping with this component of loss functions.
And do you think it would be more helpful if, like, you let the student model align to the teacher first and then learn the labels?
Oh, good question. That's what we tried to do with this tau function. So we wanted to see alignment between teacher and student is important or not. So this cosine similarity is how alignment it is between the vectors of teacher and the student. And this embedding MAE is going smaller and smaller. This is very clear. But energy, what we are targeting for, is not really going linearly with the cosine similarity of the model. So we found that the only alignment itself is not really one thing that we have to care about. but there's a sweet spot between the alignment and the accuracy itself.
Okay, and do you have an intuition why, like, aligning student and teacher is not enough? Is it because the architecture is different? Like, are you using different architectures, or?
Yeah, there's some possible explanation we can come up with, but we haven't thought about that deeply, because we tested out MACE distillation into a GemNet, or GemNet distillation into GemNet, or EquiformerV distillation into EquiformerV. Like, this kind of combination would make some discussion that could be helpful for that question, but we haven't looked into that part that much.
Did you find that? I guess you'll present it as well. I'll ask afterwards.
Oh yeah, I will show you, and you can question on later part as well. So here's the overall accuracy of the model. So when we are taking Hessian for this kind of large system, which is up to 100 atoms, they're of course going to OOM because the information is very rich. I'm using the A16 GPU for training this. And for end-to-end, it's very light to train, and it's always better to have, Oh yeah, we can try to.
Yeah, okay, yeah, makes sense. The question was, we can do finite differences, but I assume that, like, finite differences, you don't run out of memory, but you still need to do many forward passes, right?
Mm-hmm.
In the paper, there's. Okay, yeah, apparently in the paper, finite differences isn't that bad, but okay.
Yep. So yeah, that's the case for the OC20 and OMAT24. And oh yeah, thanks for the pointing out Hessian with finite differences. Yeah, I will account for it later if it's okay. And molecular system as well. So Hessian usually shows high accuracy for the small molecule system, but it was not scalable for our system such as OC20 or OMAT24. So this showcased the efficiency we can think of. And which is quite sad is that the ARC never can reach to the accuracy of teacher for energy and force of OC20 system and OMAT24, but it's always better to do the ARC or Hessian or end-to-end distillation kind of knowledge distillation compared to the undistillated counterpart. So let me pitch you. Yep.
Sorry, so here undistilled is you take do you take the student model and you train it from scratch on the, here it's like the O-star system, right?
Yep.
My question is, what if we had a new line that's it's undistilled but also trained on the teacher's model's dataset, right? Like, assume you have access. So here we're taking the teacher, which is like a large model trained on OC20. What if we took like the smaller student model and we pre-train it on OC20, and then we fine-tune on, or like even just use that student model? My question here is, like, is the goal here to have a model that's faster, or a model that's or a model that's
more on the faster part?
Yeah, because in that case, like, if we're willing to pay the cost of training the student model, we might have a student model that's because here I don't know if undistilled is, so here undistilled is that much worse than teacher, right? It's like one order of magnitude worse. But is it because we're only training it on O-star systems, or is it because that, like, the question is, has it seen all of OC20?
It haven't seen. The undistilled is only trained on the O-star cases in this case, and 200K subset of the OC20.
Right, that makes sense. And do you think if we trained it on all of OC20, it would be better?
Yeah, better. So we have evaluation study of 100K, 200K, and 2 million subsets. The subsets the Meta is giving us in their GitHub, and we test it out, and of course, 2 million is better, and longer training is better. Yeah, there's something very engineering part that we haven't really focused on.
But then in that case, like, when do you suggest using distillation techniques? In which setting?
Sorry?
In which setting is it useful to use a distillation technique? Like, which problem would you want to solve?
We wanted to have a lightweight and molecular dynamics. Of course, yeah, I will explicitly show what system I'm interested in with this smaller model. And if we can have lightweight model, we can scale in the time that it is lightweighted, and we can scale the molecular dynamics larger.
Okay.
So this is the visual representation of the table. And yeah, thank you for the ChemiFormer paper. Yeah, I will look into it after the talk. All right, so this is the energy and force compared to the teacher model. It is not quite there for the ARC models, but compared to the not distillated ones is better. And which was also work for the OMAT24 and the SPICE datasets, the smaller dataset. And good point is that we can now shrink the parameter size 7 times. We simply take out the neural network layers out to train a student model, and which can make us 7 times smaller. And this is how much we can make it better without and with ARC distillation method. And we also applied this to GemNet OC20 plus 22. And now in this case, the teacher model itself is already small, like 38.9 million to now 1.2 million. And this is one of the benchmark I showcased in the very beginning of the talk. And in this benchmark of carbon, nitrogen, oxygen binding energy calculations for catalysis application, it shows pretty good accuracy compared to the teacher model. So we thought that we can now apply this to a application, something like oxygen reduction reaction, where reducing the platinum-based catalyst is important in this task. And calculating only OOH and oxygen and OOH is good enough to get the oxygen reduction reaction activity. And this is where documented in the old papers by Professor Norskov. So they have this good linear relation, and we can come up with this 2D volcano. So I wanted to expand the search space using the ARC model. So this is one of the examples that I wanted to apply using the smaller model, the 11 times smaller model. So we take out the materials project data as well, and from these stable work structures, we come up with these surface structures of 580K slab configurations. And on that, I attached OH and oxygen so that I can get the oxygen reduction reaction activity. And here's some of the video that I screened OH and oxygen binding. And at the beginning, I calculate all the possible combination with the ARC model. And for the highly probable catalyst combination, I calculate the GemNet teacher model. And after calculating with the teacher model, for the promising ones, I calculate with DFT calculation, and finally find out the 30 DFT calculated structures is seemingly active for the oxygen reduction reaction. And this is the kind of Pokemon style of all the catalysts we found, 30 of the combinations. And we found that tellurium, including catalyst, is quite active. And there are some reports that having tellurium in the system, platinum tellurium, nickel tellurium, showcase good ORR activity. And some of the cases we found, such as silver, phosphate palladium, and palladium tellurium, all of those were also reported in the literature. So I with this list of the seemingly good catalysts, I send it to experimental collaborator and see if they are actually good for oxygen reduction reaction. So I want to summarize at this point of how we showcase this distillation method, simple distillation method of Angular distillation. for the SPICE and OMAT24 OC20 dataset, and we can reduce the size of the model 7 times while keeping the accuracy as much as possible we can, and showcase that multi-MLIP screening is possible for screening large search space and making it smaller for teacher model. And teacher model is now predicting for DFT calculation. And all of these combination can be now tested by experiments as well.
And quick question.
Yep.
Yeah, can you go back to previous slide? I think that's really cool that you can do that with a smaller model. It's really nice. I have a question. Sorry, the slide afterwards, 21. So 21, sorry.
21. One before this.
Oh, no, after.
One after?
Because you have the number on top right.
Oh, yeah.
21.
Sorry. Yeah, here you go.
Yeah, just here. So 22% energy error and 34%, for instance, for OC20. Is that on the full OC20 dataset or?
200K.
Okay, it's on the 200K and it's. So it's okay. So it's better than undistilled.
Yep.
On 200K. Okay.
Yep.
Thank you. That's cool.
And as I'm talking with Entropic literature review, and I heard that you are now shifting to ARD, and you in the website you are also interested in catalysis, battery, and semiconductors and advanced systems. So I want to showcase some of the cases we can apply this small model and the systems I'm interested in the future. So some of the systems like Seria, we can expand this small model into molecular dynamics. Like in this case, I studied Seria, where the shape of the Seria is important for catalysis, and also oxygen redox on Seria, where the oxygen uptake of the system is important. And we can also apply for sensor screening as well, as these screening search space is as large as catalyst case as well. And also for this large-scale polymer electrolyte interaction, this kind of system is also where ARC model is really capable of. And as the large language model is getting improved, now we can loop in with the large language model. And we recently made this CatAgent. So in this CatAgent, it's like Cloud Code where they're hypothesizing the combination, and using the ARC model or UMA model, they're simulating the system and is criticizing the output. So it could looping over and over again. So we found this CatAgent is finding good catalyst, and we tested by the ARC model, the distilled model, and now it can be 11 times faster with this CatAgent looping. And compared to the random baseline is twice better for the hydrogen evolution reaction. And compared with the Gemini, GPT, and Claude, we find it's clearly state-of-the-art models are twice better than just random search. And it could also apply for other absorbate as well. So we can expand to other reactions with distilled model and plus large language model together. And this is small demo we can showcase. And this is how the system itself is finding new combination with the ARC model. The speed is very fast with the ARC model. And now with the CatAgent, I'm trying to do a bunch of distillation and DFT calculation, ARC calculation with the OpenClaw and just burning tokens over and over again. And they're finding something with the ARC model. And now I let them do the DFT calculation on the systems they found. So with that, I would like to acknowledge to the co-first author who initially designed the ARC architecture, and Jinung Moon helped me for cat benchmark. And by the way, I'm going to go to ACS and IKE this year. So if you're going to go to these conferences, let's grab a coffee. And I appreciate with the National Research Funding for this. Thank you for the claps.
Great, thanks a lot. So any questions in the chat? Or Luis, do you have any question?
No, it was really clear. Thank you so much again for presenting. And yeah, I mean, here we use like the funnel approach. So it is definitely useful to have something super quick first and then, yeah, narrow it down.
So is the CatAgent that was like real time, the demo you showed?
Oh, it's actually twice faster than actual speed.
Okay,
but if you're
still...
using better GPU, then you can actually run like this.
And this was like an open source model, or this was using API calls on...
API calls.
Okay, that's very nice.
So a lot of money.
Yeah. I mean, if it finds something good, then it's worth it, I guess.
I hope so.
All right. Just maybe one quick question regarding the architecture, like the distillation method. I guess this is doing something different than distilling the Hessian. Do you think do you think there's a way to combine the two, or like, is there a benefit of one or the other based on the system we use?
Oh yeah, definitely. So for the reason we couldn't use Hessian at first, we just wanted to adopt one of the already designed architectures. So we wanted to take simply from the Hessian method, but Hessian method we couldn't scale them up on the periodic system as large as 100 atoms or 200 atoms, like OMAT24 or OC20, because the information is too rich, like not to add it to nodes. So we couldn't do that with our GPU, the A6000. And for node-to-node distillation and the arc distillation, we use these two of the loss function together. So we find this recipe during the finding the arc distillation method. So we have some ablation study in the paper in the supplementary note that simply adding these two loss functions together make it a little better in the accuracy of energy and force predictions. So this is one of the possible combination we can think of.
All right, thanks. And one other question is, so assuming we had like a big training budget, do you think it's worth it to, like, if we were able to train the student on the entire OC20 dataset again, would you recommend still having a distillation loss in the loop, or just train from scratch and enough labels would do the trick?
Oh, yeah. So another point we did this project is that from the question that how we can extract the information from trained model. So Meta put a lot of GPUs to train their models like UMA or their big models. So we want to extract the information like the previous reading group talks, like platonic representation. So this is the basic idea that we wanted to testify. So this knowledge distillation is one of the way we can extract the information from. So this is kind of not training from scratch method. So when we can scale them up, we can try this.
The question is more like, because when you don't train the student from scratch, you're taking knowledge from the teacher, and that's helpful. But the teacher has only seen a data set that currently we know, right? And that's why it's like, we know what data sets the teacher have been trained on, and we can reproduce that on the student's model. So we can take the student, just train on the exact same data set the teacher has been trained on, and let it learn something. Do you think, assuming we're able to do that, it's still worth it to distill, knowing that we have fully access to the data sets of the teacher?
If you have good enough GPU to inference teacher model, then you don't need to train a small model.
No, the question is more like retrain the student, but fully on the teacher's data set. Like, I am like, say you have an easy example is you have UMA medium, and I want to train UMA small. Should I train it from scratch using the full data set that UMA medium has been trained on, or should I use a distillation technique and train it on whatever? I mean, Ideally, I want a small
distillation
generalist model. Distillation technique on the full data set, right?
Yep.
Okay. And that would give like knowledge that the teacher model has learned and has like it's been able to compress more information that the student has been.
Yeah,
that's bigger.
What I seen for the OC20 case, as we increase the subset size from 20K to 200K to 1 million, 2 million case, the accuracy is approaching the teacher models. So if you can make it full data set, then it could maybe reach to the point, I think.
Okay. Perfect. No other question, I think. Thanks a lot, Seokhyun, for the talk. It was really interesting. And yeah, hopefully you can meet sometime soon.
Yeah. Catch up later. Bye.
Thank you so much.
Bonne nuit.